working on the Julia programming language for more than a decade now, since 2011. But I also do some other stuff. So I'm co-founder at Julia Hub, which is the company behind Julia. But sort of in my personal and now increasingly more professional life, I also have done a little bit of hardware. So my first ever job was doing PCB design. In college, I got to make my own chips. That's the wafer in the middle. And when I say make my own, I mean with spin-on photoresist in the clean room, not the fun way we get to do it now, pushing a button. And I've done a little bit of FPGA work. So the photo that's on the top right is a pretty large phased array project that I've done some work on, and that I'm going to do some more work on in the next year. But what I'm talking about today is Cedar EDA, which is an analog design verification environment, simulation environment that we've been working on for 2 or 3 years. And I'll tell you all about it, but just quickly some marketing slides that I usually show, and then I'll give you all the technical details. So as I said, I work at Julia Hub. We do the Julia programming language. We do a bunch of other things, modeling and simulation products in a bunch of domains. So we have something in pharma with a simulation product for physical simulation, so thermals, mechanicals, that kind of thing. And we also have Cedar, which I'm going to tell you more about. And that's usually the Cedar marketing slide that I show. But you all are smart people, so I can just tell you the real story rather than the marketing story. So what is Cedar? So at its core, Cedar is an analog circuit simulator. SPICE compatible, Spectre compatible, Verilog A compatible. I say compatible because sort of SPICE implies things about the architecture. Cedar does not have that architecture, and I will tell you what architecture it does have. But you can read in SPICE netlists, you can read in PDKs. It'll have support for Sky130 and GF180 automatically, which I'll show off. But it's a completely greenfield design. It's completely written in Julia. It's equation-based, not Jacobian stencil-based. So it works a lot more like Modelica-based systems under the hood, not like SPICE-based systems, although, again, it is compatible. And you can use it for the PDKs. We also have sort of a signal analysis, waveform analysis, post-processing framework. And this is all written sort of in a library-style design. So if you want to use parts of it, if you want to use the SPICE parser, if you want to use just the waveform package with some other simulator, that's all possible. So this is built as a commercial-grade system. So we are also selling this, and I'll have a whole thing on licensing later with a very special announcement just for Latch-Up. So look forward to that. But you got to sit through the demo first. But yeah, it's designed to be commercial grade. And by that I mean we are supporting customers on commercial PDKs, and we are aiming for performance that exceeds the state of the art of commercial simulators. And we're not quite there yet, so it's a little bit aspirationally. So we do have the performance that exceeds the commercial simulators, but we have some scalability issues. We have some latency issues. It does very aggressive optimization and simulation, which isn't always cached. So sometimes you can sit there for 5 minutes for it to just compile your simulation, for it then to run it in 500 milliseconds or something. We're fixing that. It'll be fixed soon. But this is sort of a preview. I'm gonna show off the tool, but I'm telling you, like, if you want to tape out something with it tomorrow, it's probably not quite ready for that. It's more mature in some weird ways that you might not expect. This was originally built as a research tool for doing machine learning-based kind of things. So if you want to do fancy machine learning integrated neural networks in your circuit, we're great at that. If you want to simulate your Sky130 design from the open source, we may be able to do it, we may not be able to do it. But we've only now sort of transitioned to making sure it's a good tool for analog circuit designers. Previously, it was mostly a research tool for doing very fancy machine learning things, which is still possible. OK, quick architecture diagram. So basically, at the core of this is a domain-agnostic optimizing compiler for equation systems. And everything feeds into this common general purpose IR. So we can import Spice, we can import Verilog A, we can import things like Modelica if you want to do multi-domain, and we can import some other native Julia formats for equation-based modeling. It all goes into a big pile of equations, and then it generates, using LLVM, very highly optimized machine code to get you really, really blazing fast. At the moment, CPU simulations, GPU support is also available. It's probably going to be the fastest GPU-based simulator anybody's ever seen, but that's not quite ready yet. OK. I want to show you the tool, and I forgot to do something at the start, so that will be done now, and then I'll switch to the. OK, so the first thing I want to show off is that it's easy to install. I think that's always a very common complaint. Oh, I'm going to make this a lot bigger. OK. All right, so I have just installed and built it on this machine. So it's super easy to install. It's available using the Julia package manager. And I'm going to do like just for lack of time, very, very small tour of the features available. Just the basic quick simulation, and I'm going to show off the GUI, and then we're going to go back to the presentation. There's a lot of features here that I'm not showing. So I'm not showing things for lack of time rather than lack of features. OK, so OK, oops, got to load it. OK, takes a little bit of time because I just added it. It's doing some compilation in the background. There we go. OK, so this is the first thing I wanted to show off. So what am I doing here? I'm just loading simple Spice netlist. I'm sure all of you have seen it. We provide a string macro interface. You can just dump your Spice netlist into a source file, and it'll give you a representation of that Spice netlist that the simulator can work with. One particular really cool thing I wanted to show off is the package manager integration for the PDKs and anything else you might want to put in a netlist. So it's a little hard to read here, but basically I had a .lib statement that referenced a PDK provided as a Julia package, and then it said, you don't have this PDK installed, you want to go ahead and install it, and you can just say yes, and it'll go and download the PDK and install it, and just keep going from there. So there's no manual setting up paths and PDK installation. If somebody sends you a netlist that supports this format, it'll go and do that. OK, and it'll take some time to download, so I prepared ahead of time, and already did this in the other window. OK, so just the standard things you might expect. I can do a tran bang of this circuit. And I don't know why it thinks it needs to compile this. It should have already done that. OK, there we go. So what you get back from this, too large on the screen. But what you get back from this is not just the raw numbers, although they're in there, but you actually get a standard in the Julia ecosystem. There's a standard set of packages for modeling and simulation, and this integrates with that. So this is a standard solution object that works with all the standard post-processing for simulation that we have in the Julia ecosystem. So just to show that off, there's a cool package we have called Unicode plots, which will plot in the terminal. So I'm just going to show, sol inverter D. OK, there's my inverter input, and there's my inverter output. OK, and I apologize if this is hard to see on the screen. OK, anyway, that's the quick demo of capabilities in the. Oh, I think I closed that tab. In the terminal, let me. So that's not what we ship to customers. What we ship to customers is a cloud-based GUI thing, which I accidentally closed before I came up here. But in any case, We ship this to customers in a cloud-based GUI environment, and I wanted to do this demo, although it might take too long to run since I accidentally closed it. If it takes too long, we'll get back to it. Sorry, this was planned as 30 minutes, so I'm going a little fast. I apologize for that. But yeah, so this takes like, I think, 2 or 3 minutes to run, so I might go back to the slides and then show off the rest of the demo. But basically, it's available as a command line thing. It's available in an integrated cloud environment, which combines the simulator with the post-processing environment with a bunch of other things into sort of a productionized thing that we sell to people. OK, I'm going to just leave that running and go back to the slides and tell you about licensing, do the special announcement, and then go back to the demo. OK, licensing. So this is the licensing we've had so far. The special announcement is about licensing. So this is free, has been free for people doing open source silicon. We've had people on the platform for about 2 or 3 months, just sort of people playing around. Again, it's still early, so we haven't really rolled it out super wide. We just wanted to make sure that we have the ability to support people. As I said, we also sell this commercially. We've shipped it to commercial users last year. And the commercial license is available for people who want to build on proprietary PDKs. OK, special exciting announcement. As of this morning, it's on GitHub. I saw some very skeptical faces when I saw commercial. So it's on GitHub, but it's not public yet. It is public. All right, OK. Right now. OK. So that's the special announcement. So what are we doing with the public release? So the source code is available, basically all of it. So all the secret compiler special source, it's up there. You can see it. We put a license on it of the CERN open hardware license. This is very explicitly a licensing experiment. The CERN open hardware license was not designed for EDA tooling. In fact, CERN explicitly tells you not to do this. I've talked to a lot of very expensive lawyers, and I asked them if I could do this. And they said, well, nobody knows. But if you want to risk it, you can try it. So we're trying it. The idea behind this is if you're building open source hardware, open source silicon, treat it as an open source project. Use it, read it, contribute to it, change it, fork it, build other things on it. We don't care. If you're building on proprietary PDKs, if you're building proprietary chips, we'd like you to pay for a commercial license. And we want to make this sustainable. We want to make sure that modern, exciting EDA software exists. We want to make sure that it keeps existing, so I can pay people to do it. So that's the deal. You guys get to use it for free. Other people have to pay. We'll see if it works. It's an experiment. We'll evaluate it. We'll see if it works. We'll see if the open source community likes this. We'll see if the commercial people accept it. And we're happy to work with people. If you say, look, I'm an educational institution. I'm on a proprietary PDK, but I can't afford to pay commercial license fees. Work with us. We'll work it out. I also made a lot of the non-core pieces MIT. So if you want to build a Verilog A language server using our Verilog A parser, you can do that. If you want to use our BSIM4 model, which is ported to Verilog A, and you want to run it through OpenVAF and run it with some other commercial open source simulator, you can do that too. There are some asterisks. So obviously, the proprietary PDK support is not part of this. If you want proprietary PDKs, get a commercial license, sign the various NDAs. Other Julia Hub products are also not part of this, at least at the moment. If this works well, we might expand it. But so if you want to do multi-physics things, not part of this, although you can use the thing that I mentioned previously where there's a Julia Hub open source hardware version of this where it's free. And we might, we'll figure out if you want to do that, let me know. We'll figure out the licensing for that. Also not part of this, fancy machine learning things that people want to do, which is a different Julia Hub product. So basically, it's just the circuit simulator that's part of this announcement. But it is the full circuit simulator. It's everything. It's all the PDKs. It's the compiler internals. It's the optimizer. It's everything that makes it fast. OK. Now, I will show the rest of the demo. I apologize. The demo is not as exciting as that announcement. So, so this is sort of a more typical use case. This shows off our post-processing environment as well as our sort of validation APIs. So this is a netlist just from GF180. It's one of the D flip-flops that's in the GF180 PDK. So not huge, but not tiny. And then what are we doing here? We're defining that for this particular circuit, we have design constraints on rise time and delay. So you can specify a set of measurements, and then you can either interactively explore the measurements, or there's also a bulk API. If you want to do CI/CD for your designs, you can do that too. So I hope this works. And oops, of course it does not. Let me see if I can just reload the plot. Yes. OK. So this is sort of a thing that somebody might do. You can scroll through design. You can scroll through design space. The two parameters are just some capacitors I added to glitch and to. So the first one is the load capacitance at the end, and then there's a glitch capacitance that bypasses something. So you might interactively explore your design space, and then it'll tell you if you violate any of the design constraints. And again, there's a batch API to this also. So a fairly common use case is you batch this, and then you get a violation, and then you go into the interactive thing to interactively explore the failure. OK. That's all I have. I mean, there's lots of extra features. There's lots of things around differentiability and machine learning integration. As I mentioned, we have a source level Verilog A debugger. We have live reloading of Verilog A if you're developing Verilog A. We have lots of things. It's all up on GitHub. There's documentation also up. I will say that I probably messed something up moving it to GitHub very frantically this morning. So if you try it right now, it might not work, but we'll clean that up over the next couple of weeks. Make sure it's working well, and we hope you use it. Again, it's an experiment. This was and is still a commercial product, but I'm personally very excited about open source silicon. I'm excited about the open source silicon community, and I hope we can help. So, any questions?
I'm sure there will be questions. I have a quick minor trivial one. Is Global Foundries 180 open? Have they released that?
Yes.
OK, all right. I missed that. Sorry.
Hello. Thanks for the presentation. So my question is, from what I know, Julia is usually used for more like data science, scientific computing codes. So it was very interesting to see used for a simulation. So was there some interesting insights when you build it, on using Julia as a language for building a simulator?
OK, so Julia has quite a sophisticated simulation ecosystem. So there's the SciML organization, which stands for Scientific Machine Learning, but they also have differential equation solvers and various modeling and simulation, like post-processing and analysis and all of that. So Julia is fairly well established in modeling and simulation. The unusual thing about this is the compilation piece. So we really wanted to make sure that the performance of this was absolutely top. So there's a really, really sophisticated optimizing compiler in here. And it's unusual because it reuses the Julia compiler internals for compiling something which is not Julia. So it's compiling Verilog A, it's compiling Spice, but that is something quite unusual about the way we set this up, is that we're actually reusing the compiler for something that wasn't designed for. Although I wrote the compiler, so I guess it's designed for it now.
Question. So you've shown this running in various environments and
yes.
cloud servers. Is it possible to just run this thing in batch, like a complete replacement for a similar simulation in ngSpice or something?
Yeah, so it's possible, yes, but if the way you're setting it up is that you're sort of wrapping like a bash loop around every single simulation, you probably will get suboptimal performance. So what we'd like the way it's designed is that if you're doing a sweep, we want you to tell us what variables you're sweeping so that we can compile an optimized version of it that lets you sweep that very fast. And we can sweep everything. So we can sweep like arbitrary Spice parameters without re-elaboration because we compile not just the Verilog A, we also compile the Spice, like the inline expressions for computing Spice parameters. So if you tell us what you're sweeping, we can do a much better job in terms of performance. And depending on whether or not your existing simulator can do those sorts of sweeps without re-elaboration, like we can be thousands of times faster on those sweeps by just putting the inner loop of the sweep inside the simulation.
And you can run post-processing and dump to a file?
Yeah, if you want. I mean, like it's fully integrated with the Julia ecosystem. So like any file format you can imagine, we have writers for, just because you get it in a table object. So if you want CSV, if you want Parquet, if you want Feather, if you want to write it to a SQL database, it's all possible.
One last question.
It's more of a Julia question.
Yes.
Do you see a day when you'll have like a monolithic Julia kernel or an OS or an ASIP or something, or maybe there's some work already in that space?
Well, I mean, we have most of a Linux distribution, and every once in a while somebody threatens to write a C library, so who knows?
All right, let's all thank Keno again. Thank you very much. Great presentation.